Okay. Hello, everybody. This is an experiment showing how I might illustrate the process by which I would solve particular problems using the expert TA system. This is just practice, and it will consider one of the problems I already solved in class on Friday before break. Uh, the goal here is just to see how this system might work and for you guys to suggest any improvements you might find. So let me know what you think about this. Basically, we have the expert TA window sitting over here, and we have some white space here to work on the problem. The problem here is stated as follows. An MRI technician moves his hand from a region of very low magnetic field strength into an MRI scanner's 2 Tesla field with his fingers pointing in the direction of the field. His wedding ring has a diameter of 2.05 centimeters, and it takes 0.325 seconds to move it into the field. The question we're trying to answer is, what is the average current induced in the ring if in amperes if the resistance is 0.01 ohms? So what we're going to do is use the same procedure we've always used for these sorts of problems. Again, we first write down, and this will be slightly goofy writing because I'm doing it on the screen. The first thing we always have to write down is what are we looking for? In this case, we're looking for the quantity I, the current, and we don't know what that is. So put a little question mark here. So that's the thing we want to know. What are the things we know? Well, we can look through this. We know that the magnetic field, B, that we stuck our hand into, or the person stuck their hand into, is about 2 Tesla. So that's one thing we know. We also know that his wedding ring has a diameter, which I'll just write as D, is 2 centimeters, but we can also write that as 0.0.0205 meters. Fine. We also know the time it took to stick one's hand into this thing, which we'll call t, is 0.325 seconds. So 0.325 seconds. And of course, if this is hard to read, let me know and we can try and figure out something better than that. We also know that the resistance of the ring, which is capital R, is 0.01 ohms. Okay, so those are the quantities we immediately know. The next trick, as we've always talked about, is we need to find a relationship that connects what we know to what we want to find. And this is one of those problems where that's not obvious. We don't have a single relationship that connects current to magnetic field, resistance, time, and size. The first relationship but there are a couple of relationships we can combine to do that. The one that kind of stands out is we're told the resistance of the wire and we're looking for a current. One of the things we have that involves both those quantities is, of course, Ohm's law. V equals IR, which we can always just rewrite as I equals V over R. Fine. This, now, again, though, so we know we want I and we know R, that's good, but we don't know what V is. We don't have anything in here that immediately tells us what the voltage is. The critical thing to understand, though, is we do have a relationship for that. That is no longer in volt. This voltage isn't just V, it is also this quantity we've called EMF. And we know from Faraday's law that EMF, which is also voltage, is equal to minus n, the number of loops, times the change in the magnetic flux, delta phi, which is a rather complicated sign to draw, per delta time. Okay, so that seems like it's relevant because we are talking about magnetic fields here. Now, there's a new quantity here, n. Do we know what n is? Well, in fact, we do. A simple ring is just a single loop. So we do actually know what n is. It's just simply 1. So we know what that is. What's the change in time? Well, we have a time here that is the time it took to do things. So we can say that's the delta time. But what's the change in the magnetic flux? Well, if we think about this, this is not really the absolute, this is the magnetic field we stuck our hand into, but it's also the change in magnetic field, since we started from a place where the magnetic field was 0. So we know what the change in B is. And we know that flux is basically given by the magnetic field strength B times the area of the loop A times the cosine of the angle between them. These are all things we've done in class. Now, the angle between them, do we know what that is? Well, yes. The person's fingers were pointing along the direction of the field line. So if we had a person's hand that looked something like this, their ring would look, let's see if we can do this. Their ring would look something like this. And the magnetic field going through this is aligned with the person's fingers. So they would look something like this. So the magnetic field line is going straight through the ring. Cosine theta is 1. Basically, theta is 0. So we can get rid of it. So we can just replace that with cosine theta being 1. So what that means is that in this particular case, going back to proper color, the delta phi we have is the change in the magnetic field, delta B, which we know, times the area of the loop times 1. Well, we know this. Do we know the area of the loop? Yes, because we know the diameter of the ring. The area of the loop will just be pi over 4 times the diameter squared. That's the area of a circular ring. And you can look that up if you're worried about it. So now we've got something that just involves delta B and T, so we can figure out this. We know delta T and N, so we can figure out this. We know R, so we can figure out this. So we can combine all of these expressions to get an expression for I. I is going to be N, basically V, the potential, which is also the EMF, which is going to be N delta phi, which is delta B, pi over 4, d squared, divided by delta t, but also divided by r because of the original Ohm's law. So this is the expression we can have. Now, some of you might notice, wait, what about the minus sign? The minus sign just tells me what direction the current flows, not what the current is. So that's not particularly relevant for this particular part of the problem. It might come in later. So that's what we think the expression ought to be. And it makes some amount of sense. If you increase the magnetic field, you'd expect the current to be stronger. If you make the resistance bigger, you would expect the current to be weaker. So let's try this out. Let's try and enter the numbers. So we have n, which is 1, times the change in magnetic field, which is 2, times pi over 4, times the diameter squared, which we've got to remember is in meters, divided by 0.325 seconds divided by zero point zero 0.01 ohms. And we'll just submit that, see what we get. You get a grade of 100%, so that was correct. That works out to be 0.2 amps, which is a fair amount of current to be running around a wire ring on your finger, and might be something you would notice. So that's how we work through that sort of problem. And it's a little complicated because you had to think about what would give you each one. And there's multiple relationships that allow you to get the quantity you want from the various things we have. But hopefully this isn't too surprising. Anyway, let me know what you think about this particular video and things that could be done to improve it. And we'll see about whether we'll go along with this or use something else in the future. Thank you very much for your time.